Let fx equal to defined by this structure and x is coming from closed interval this. Then which of the following is true? Maximum value of fx is 3 by 2, minimum value of x is 1 upon 3, maximum at half and minimum at 1. Means four options are related: maximum value and minimum value at a point, or maximum value at a point. Means minimum value and minimum at a point, maximum value and maximum at a point. These four types of options is given to us. As fx is 1 upon 1 plus mod x plus 1 upon 1 plus mod x minus 1, and this is true for all x is coming from closed interval minus 1 to 1. Whenever absolute function involve, then always break absolute function at that point from which behavior changes. So we know very well at point absolute value changes. So fx can be written as for positive and negatives. Means whenever x is less than 0 and greater than minus 1, because of minus 1 is the left bound of this interval. So fx will be 1 upon 1 minus x plus 1 upon 1 plus of x minus 1. It is for negative value, means for negative value this is also negative, so absolute value is minus of x, and it is also so minus of minus x it. And for positive value, so first is, suppose this is for negative value, so I can write 1 upon 1 minus x plus 1 upon 2 minus x. This is for negative x. And for positive value, means x is greater than equal to 0 and less than 1, so it will be 1 upon 1 plus x for positive value plus 1 upon, this is again 2 minus x. So I have this function, this is my fx. Now f dash x will be derivative of this one will be minus of 1 minus x derivative and again positive, so 1 upon 1 minus x whole square plus 1 upon 2 minus x whole square. This is the derivative for negative x, and for positive x it will be minus of 1 minus 1 plus x whole square plus 1 upon 2 minus x whole square. This is for positive x. And I left at 1 because I didn't take at 1 because of function can change at boundary points. Function can change behavior at boundary points, so I left this 1 at interval. So I define f dash x at minus 1, so you can remove this one inequality also, means minus 1 to 1. This is, so at 0, at this point is 0, this value is 1 upon, so minus 1 plus 1 upon 2 square, it means negative. So at 0 f dash is less than 0. F dash x is less than 0 when x equal to 0. But uh, we surely have the conclusion, or we have conclusion for positive, sorry, for negative function is increasing. For negative x, we know function is increasing because of this is positive value always. It means minimum value, minimum value because function is increasing, because function is increasing from -1 to 0, like this or this way. It means minimum value will exist at this point if function have the same behavior, means monotonically behavior, then function have minimum value at -1. And this option D is saying minimum value of fx occur at x equal to 1. So this is false statement. If function have minimum value at -1, then value of the function at -1 will be 1 upon 1 minus of -1 plus 1 upon 2 minus or plus 1. You can write. It means 1 upon this is again 2 plus 1 upon 3 means this is not true. Minimum value of fx is 1 upon 3. This is false statement. Means we have two remaining options A and C. Maximum value of fx is 3 by 2 and maximum value at half. So we all know function is increasing for this point. So consider function is increasing. Function is increasing or say monotonically over the closed interval -1 to 1. If it is increasing, because half part is increasing, so I consider or let function is monotonically increasing on the entire domain. So if it is increasing, then value of the maximum value of the function is at 1. So max value will be at 1. So 1 upon 1 plus 1 plus this, it means 1 upon 2 plus 1 equal to 3 by 2. So maximum equal to this matrix, and alpha which is used in this matrix is non-zero real number, and b a non-zero vector means column vector, you can understand, such that mx equal to v for some, this is important terms, for some x belongs to R cube, then the value of x transpose b is, the value of this one is what? Is negative of alpha as used in this, alpha 0 or 1. As this matrix representation for a system of linear equation, this is a matrix representation mx equal to b, matrix representation of linear system or linear equation or system, linear equations. So b is a column vector, you can understand in earlier classes. This is again column vector, and this is given matrix M. This is given matrix M. This column vector is coming from R3. So consider a column vector for M
This is x1, x2, x3. This is column vector, and vector v, b1, b2, b3. So mx equal to b is justified here, but keep remember, for some x belongs to R cube, means this is true. Both left hand side equal to right hand side is true for some x belongs to R cube, means this is the solution, means some column vector which satisfy this equation will be exist. It means this system is consistent, and the condition for consistent is rank of rank of co- coefficient matrix is equal to augmented matrix rank of augmented matrix. This is a condition in terms of rank. System is consistent. So write the system and row reduced in echelon form to predict the answer. Matrix M as 1, -1, 0, 0, 0, 1, 0, alpha, -2, 0. This is a matrix. B2, B1, and this is B3 plus 2 times B2 plus 2 times B1. This is a matrix, row reduced matrix for given matrix. So what row operation I applied? First, replace second row by first row. Means this is -1 should comes in first to make first non-zero leading element or non-zero leading entry, and then make 0 under that leading entry. This is the procedure. So after applying row operation, you will get this matrix, and this is a system and consistent system. So this is coefficient matrix left to this line, vertical line. This is coefficient matrix, and if we add this one also, then this is augmented matrix. So rank of this one will equal to rank of this one when this is a 0 row in coefficient matrix. If this number or this entry becomes 0, then rank of coefficient matrix and augmented matrix will be 2. So B3 plus 2 times B2 plus alpha, I think I did mistake here. This is alpha. Alpha B1 equal to 0, and x3 is free variable. This is x3 because x1, x2, x3 are constituent of the column vector or solution. So x3 is free variable. So b3 can be written as negative of 2 b2 minus alpha b1. This is b3, and from this system as circular part, this implies that minus x1 plus alpha x3 equal to b2, and second is x2 minus 2 x3 equal to b1. So these two implies that x1 equal to alpha x3 minus b2, and x2 equal to b1 plus 2 times x3 means, and x3 is free. So all constituent of solution vector we have means x1, x2, x3, and we have to find value of this one with column vector b1, b2, b3. What is this? So write this one as alpha x3 minus b2, b1 plus 2 times x3, and this is x3. This is solution vector, and this is right hand side of vector. So take transpose of this one b1, b2, b3. So we will get, so write this one as a row vector. So alpha x3 minus b2, b1 plus 2 times x3, and this is x3. This is as a row vector. This is x3, and this is column vector b1, b2, b3. Now these two are compatible for multiply. So multiply these two. We will get, this is a single row and this is single column. So we will get alpha b1 x3 minus b2 b1 plus b1 b2 plus 2 times b2 x3 plus b3 x3. So this is the value we obtain after multiplying these two row vector and column vector. So this is alpha b1 x3 minus b2 b1 plus b1 b2 plus 2 times b2 x3, and what is the value of b3? Here you can see as this, I can change the color as blue circle part. This is the value of b3 used here. So b3 will be, so minus of 2 times b2 x3 minus alpha b1 x3. So all these terms will cancel out by each other. So value of this is 0 or 0 vector or 0 matrix. So we can simply write 0. So option C is correct. The number of group homomorphism from the cyclic group Z4 to the cyclic group Z7 is, in general, given information is cyclic group over cyclic group Zn, and this group is cyclic as well as abelian with respect to operation addition modulo n. Now the number of group homomorphism from the cyclic group Z4, suppose this is a function from Z4 to Z7, the number of group homomorphism can be easily find out by GCD of, if this is M or N, then we can in general find the number of group homomorphism by GCD of Mn. This will give you number of group homomorphism, as this question is particularly asked about Z4 to Z7. Then number of group homomorphism is by GCD of 4 and 7, and this is 1. So option D is right choice.
Let f is a function defined as this. At x equal to 0, the function f is continuous and differentiable when alpha is 0, continuous and differentiable when alpha is positive, continuous and differentiable when alpha is lies between -1 to 0, continuous and differentiable when alpha is less than -1. Means in all four options we have to check continuity and differentiability of the function for particular or certain values of alpha. So for continuity there is no need to check, because if function is differentiable then we know that function is continuous also. So I'm going to directly check differentiability at 0, but you can check continuity of the function as limit x tends to or h tends to 0 negative f of x, and this one is equal to limit h tends to 0 f of 0 minus h, and 0 minus h is nothing but limit h tends to 0 f of minus h. And because function is defined for not equal to 0, so it will be minus h, and inside this bracket 1 plus x raised to the power alpha sine of ln x square, and this h involved. So when we take limit h tends to 0, entire one goes to 0. Similarly, for right hand limit, limit h tends to 0 positive f of x, again this one will go to 0 because of h. So function is continuous whatever the value of alpha. Function is continuous means f is continuous for all alpha. Now we are going to check function is differentiable or not. So first left hand limit will be limit h tends to 0 f of 0 minus h minus of f0 divided by minus h, and this one equal to limit h tends to 0 f of minus h minus f of 0 divided by minus h. So this value of the function at 0 is 0. So this is a limit h tends to 0 f of minus h divided by minus h, and f of minus h is minus h, and this divided by minus h, so minus h cancel out by this one, and left one will be limit h tends to 0 1 plus minus h raised to the power alpha sine of log of minus h square, and because h is here and sine is oscillatory function, so limit of this one is goes to 0, and 1 plus 0 is nothing but 1. Means LHD or right, LHD left hand limit is 1. Also right hand limit RHD will be same as 1. You can check. So LHD and RHD, we find directly RHD from this expression because of minus h replaced by h, so you will get 1 again. So RHD is also 1, and these limits are free from alpha. So function is differentiable everywhere. Sorry, function is differentiable at 0 for all values of alpha. Means all four options are true. All options are true. Let Sn be a sequence of positive real numbers satisfying this relation for all n greater than equal to 1. If alpha and beta are the roots of this equation and satisfying this condition, then which of the following statement is are true? Sn is monotonically decreasing, Sn is monotonically increasing, limit of this sequence is alpha and limit of this sequence is beta. Means we have to tell about two things of the sequence is monotonically increasing or decreasing, and limits of the sequence, meaning converging point of the sequence. The beauty of this question is as x square minus 2x plus 3 by 4 equal to 0, and sequence is 2 Sn plus 1 equal to Sn square plus 3 by 4. So this sequence is somehow obtaining by adding the terms of this equation. As alpha beta are the roots of this equation, it means that 4x square minus 8x plus 3 is equal to 0. And to find the roots of this quadratic equation, we factorize it. So 2x minus 1 and 2x minus 3 are the factor of this equation, and x equal to half and x equal to 3 by 2. These are the roots. As it is given that S1 is less than beta and greater than alpha, so means alpha is less than beta. So by intuition, we can say this is alpha and this is beta. So alpha is half and beta is 3 by 2. So first term as given, S1 is less than 3 by 2 and greater than half. Now we are checking that what about other terms. So first for S2, so S2 is will be because S1 is square plus 3 by 4. So make a square of it. It will be 1 upon 4 less than S1 square less than 9 upon 4, and add 3 by 4 both sides, means in whole inequality. So it will be 1 less than, it will be 2s2 less than 3. So s2 is less than 3 by 2 and less than half after dividing by 2, because 2 is positive, so sign of inequality doesn't alter. Means s2 is also lies between 1 upon 2 and 3 upon 2. So similarly you can verify that other terms will also be lies between 3 by 2 and half. Means sequence is bounded. Sequence is bounded. And for monotonicity, we will seek sign of derivative and its double derivative. So we can easily tell about is sequence is increasing or decreasing. As sequence is terms of the sequence defined as 2 times Sn plus 1 is equal to Sn square plus 3 by 4. So set, as this is input and this is output, so set Sn as x and Sn plus 1 as y. So it will be 2y equal to x square plus 3 by 4. So differentiate this equation with respect to x. So 2 times dy upon dx equal to 2x. Derivative of constant term will be 0. It means that dy upon dx equal to x. Means sign of derivative doesn't change. Means this sequence is monotonic. I'm not saying increasing or decreasing because sign is same, monotonic. And d2y upon dx square is equal to 1 means greater than 0. This is saying that positive, so decreasing means bounded and decreasing monotonic, bounded plus monotonic decreasing sequence. So it will be convergent. If sequence is convergent, then find the limit of the sequence. So limit of Sn will be lower bound, or because all terms is lies between 3 by 2 and half, so this is lower bound. So limit of Sn is half. Now check the options, and half is alpha, so option C is correct, and Sn is monotonically decreasing, so option A is also correct, because limit of Sn is half and half is the value of alpha, so A and C are correct. Let f is a function from R square to R defined by this structure. At the point 0, 0, which of the following statement is are true? F is continuous. F is continuous. Sorry, first option is f is not continuous. Second option is continuous. F is differentiable. Both partial derivative of f exist. Means we have to check continuity and differentiability of this function and partial derivatives of this. So function is given by f of xy is given as xy upon mod x if x is not equal to 0 and 0 elsewhere. This one can be written as xy upon x if x is positive, and xy upon minus x if x is less than 0, and 0 elsewhere. So x cancel out by this and this one. So we obtained y when x is positive minus y when x is less than 0 and 0 elsewhere. So this is our function xy. Now we have to check continuity of this function at 0, 0. So we have to check limit xy x comma y tending to 0, 0 of function. So as left hand limit or right hand limit we can check. So we have to check continuity of the function, so we can't approach as 0, 0 from all directions, so we can consider along the line y equal to mx. So y equal to mx is sufficiently many times we can check, so it can be limit x and mx tending to 0, 0, or finally x tending to 0 of f of xy. If x tending to 0, it doesn't mean x is greater than 0 or x is less than 0. So limiting value is 0. Similarly, when we will approach this point from right hand side or left hand side, so finally limit we have 0. Now we have to check partial derivative, means function is continuous at 0, 0, we have to check partial derivatives of this. So f of fx at 0, 0, so it can be explained by limit h tends to 0 f of 0 plus h comma 0 minus of f 0, 0 divided by h, and this one can be written as limit h tends to 0 f of h comma 0 minus f 0, 0 divided by h. As h tending to 0, it means h is neither positive or negative. So by the structure of f, as we explained earlier, this is 0 minus 0 upon h, so 0. Never understand this as 0 by 0 format, because we obtain 0 by 0 format after putting the limit, but without applying the limit concept or taking the limit, we have 0, so final limit is 0. So fx exists, so fy 0 0 will be limit k tends to 0 f of 0 comma 0 plus k minus f 0 0 divided by k. Similarly, f 0 k minus f of 0 0 divided by k, and we have to find limit k tends to 0. And this one again, k tending to 0 means the x coordinate is 0. X coordinate is 0, so 0 minus 0 divided by k. So again we obtain the limit 0. Means partial derivative exists at 0 0, also function is continuous. So option B and D are true. Which of the following statement is are true? There exists a connected set in R which is not compact. Arbitrary union of closed intervals in R need not be compact. Arbitrary union of closed interval in R is always closed. Need not be compact, always closed. So B and C are somehow correlate. Every bounded infinite subset V of R has limit points in A itself. So we will check each options one by one. Option A, there exists a connected set in R which is not compact. Connected, we need to find connected but not compact. But not compact. Compact means closed and bounded. Closed and bounded. Closed means all limits points exist in the set. We know that intervals of R or real line is always connected. So there exists a connected set in R which is not compact. This is open interval AB. This is connected, connected but not compact, but not compact, because this is not closed. Now come to the option B. Arbitrary union of closed interval in R need not be compact, and C option say arbitrary union of closed intervals in R is always closed. So consider, suppose this is closed interval 1 by n to 1, or you can take any point here. So arbitrary union of A means those set, suppose 1 by n to 1, union of this one is 0 to 1. Semi open interval 0 1, this is connected, this is connected but not closed, but not closed but bounded, also bounded, also bounded. So always closed, so statement C becomes false here, and option B need not be compact. So here it is not compact because of not closed, so not compact. It is not necessary, it is compact, so need not be compact. So this is statement, because of the word need not, it is becomes true. Option D, every bounded infinite subset V of R has a limit points in V itself. So bounded and infinite subset of R. So again consider open interval this, it is bounded, yes it is bounded. Infinite, again but limit point a and b not belongs to closed interval ab, not belongs to closed interval ab. And option D is saying every bounded infinite subset V of R has a limit points in V. So if this is V, so limit points are not in V. So this statement is again false. So correct statement is A and B. Let Px equal to 5 upon 13 raised to the power x plus 12 upon 13 raised to the power x minus 1. And this function Px is true for all x belongs to real number. Then this equation Px equal to 0 has exactly one solution, means one root in R, is strictly increasing for all x belongs to R. Equation Px equal to 0 has exactly two solution or two roots in R, means real roots. Px is strictly decreasing, means we have to find or check two things. First is Px is either increasing or decreasing, and second is roots of Px equal to 0, means real root, only one real root or two real roots exist for this equation Px equal to 0. As for increasing or decreasing, we will check first derivative. So Px equal to 5 upon 13 raised to the power x plus 12 upon 13 raised to the power x. So take its derivative. So p dash x, a raised to the power x, derivative of a raised to the power x is a raised to the power x log a. So apply this formula. So 5 upon 13 raised to the power x log 5 upon 13 plus 12 upon 13 raised to the power x and log of 12 upon 13. And derivative of minus 1 is 0. As we know that 5 upon 13 is less than 1 and 12 upon 13 is also less than 1, and graph of log function is goes like this, and value at 1, log 1 is 0, and value less than log a, when a is less than 1, is negative. So this is negative value and this is negative value. So entire p dash x is less than 0, and this is true for all x real x, means px is decreasing. Px decrease in two ways. First is in concave, and second is like this. If a real roots exist, it means that only one real root will exist. So we will check is roots existing or not. As Px is given 5 upon 13, 5 upon 13 raised to the power x plus 12 upon 13 raised to the power x minus 1. So consider t is the root, t is the real root, t belongs to real. So pt equal to 0 implies that 5 upon 13 raised to the power t plus 12 upon 13 raised to the power t equal to minus 1 equal to 0, and take minus 1 in right hand side, so equal to 1. So this is true when t is 2. Why? If 5, 12 and 13, these are Pythagorean triplet. We know that these are Pythagorean triplet. So consider this is 5, this is 13, and this is 12, and this is 13. So sine theta L upon K or P upon hypotenuse, and P is 5 and this is 13. Cos theta is 12 upon 13, means base upon hypotenuse B upon H. So this PT, this PT or P theta in terms of theta, so we can write P theta is sine raised to the power t, or this plus cos raised to, you can write pt instead of theta because power is in t. Cos raised to the power t theta is equal to 1. So this trigonometric identity is true when t is 2. So only one real roots exist, means value of t is only 1 and this is 2. So which one or option is true? The equation px equal to 0 has exactly one solution in R. It is true. Px is strictly increasing. This is false. Px has exactly two solutions. This is false. Px is strictly decreasing. It is true. So option A and D are true.